In this video, I'm going to present the recent work we've published in the Journal of Machine Learning Research, and that was done with Luong and Nguyen, Analytically Tractable Hidden State Inference in Bayesian Neural Networks. So first, let's make a quick review of the nomenclature of neural network, especially feed-forward neural network. So what you see here, what we use as the input nodes are denoted by these pink round nodes that represent the input layer or covariates of our neural network. Then in blue, what is denoted by A are our activation units. And in neural net, activation units are nonlinear transformation of Z, which are denoted as hidden units. So here the superscripts for my activation units or the hidden layers to which they belong. So these are the activation units belonging to the G hidden layer. And the subscript here represent which specific activation unit we're referring to among or within a hidden layer. Same for the hidden units. So as I said, hidden units here, they are overlaid with the activation units, and we can go from the activation units at a layer J-1 to the activation units at a layer J-1 to the hidden units at the Jth layer by multiplying each of those activation units on the previous layers times the weights that are represented here. So each weight represents one activation units on the previous layer. And once we've summed all those pairwise product, we add a bias term. That's going to give us the hidden units at the subsequent layer. Okay, this is a standard practice for feed-forward neural net. And at the end, we have L hidden layer, and at the end we have an output layer where the number of node is dictated by how many output we want on our neural net as a function of how many observations we have available to train the model. And this was the kind of expanded representation of our feed-forward neural net. What we're going to use in this presentation from now on is this compact notation where each of the either input layer, hidden layers, input layer, hidden layer, or output layer are going to summarize by vectors here in this compact notation, where note that thetas regroup all the parameters in our network, either the weights or the bias that belong to any of the hidden layers. Okay, little overview of the field of Bayesian neural network. So let's say that we have a set of data consisting of pairs of covariates and observations, and we have a set of D of those pairs. So what we want to do with Bayesian neural networks is to use Bayes' theorem in order to infer the posterior for all of our parameters defining the weights and the bias in our network given the data. So this is a function of the prior knowledge for the weight and bias times the likelihood of predicting the data given the parameters divided by the normalization constant or the evidence. But the issue with this is that doing this has long been considered to be analytically intractable for neural networks. So there's been many methods over the years that have been proposed to overcome this limitation. First, simple-making approach based on MCMC or especially HMC, Hamiltonian Monte Carlo. But the main limitation is that these approaches are computationally expansive for large data sets. There's been some variational inference approaches where we assume that the posterior distribution that we're trying to infer here is approximated by a known family of distribution for the parameters, for instance, the normal, and the hyperparameter of that distribution, for instance, the mean vector and covariance matrix, are called eta the hyperparameter. And with variational inference, we try to optimize these hyperparameters via a gradient-based approach. The difficulty is that it's typically hard to optimize and difficult to scale. Then there are some ensembling approach, such as MC dropout or deep ensembles, where we try to ensembles or to regroup multiple predictions from different neural networks, but this is typically also computationally demanding, and inherently it does not consider the epistemic uncertainty about the parameter of the network. So we don't have explicitly a posterior for our parameter. We just have a posterior for our prediction, the outputs of the network. And these challenges, these limitations from these models that we addressed with a recent paper we published, Tractable Approximate Gaussian Inference, TAGI, where what we can do is we can do Bayesian analytical inference for theta, the parameters of our neural net. And we can do this with a linear computational complexity with respect to n, the number of parameters in our neural net. And this is the exact same complexity as backpropagation neural networks. The key is that there are no gradient backpropagation whatsoever that is required because everything relies on Bayesian analytical inference. We can handle end-to-end treatment of uncertainty on all the architecture we've tested so far, which are feed-forward neural nets, CNN, GANs, reinforcement learning. The performance of TAGI trained architecture is either equal or better than backprop trained networks. And finally, a key point also is that there are, with TAGI methodology, far fewer hyperparameter than the equivalent backprop trained architecture, so much less time required in order to tune those hyperparameters. So if you want more detail about this, the paper is available in JMLR. So today's talk is going to be, first, we're going to review the key notion associated with TAGI in order to build on it. Because what we want to show is that not only we can infer the parameters of a neural network using TAGI, we can also infer the hidden states associated with a neural network, okay? And this, what we're going to see together today, is that it enables a paradigm shift for several applications, such as adversarial attacks, using a neural network as a black box optimization tool, and finally for continuous action reinforcement learning. Okay, so first thing we're going to see is a review of TAGI tractable approximate Gaussian inference. So it relies on the Gaussian conditional equations. So Gaussian conditional, it allows us to, if we can model the joint probability as a joint normal for our observation and parameters, we can then also use the Gaussian conditional, meaning that we can condition on the observation to have also a closed form solution that is as well normal. And the key of this is that this inference is analytically tractable and scalable. This is the same thing that is used in state-space model, Kalman filter, Gaussian process regression, for instance. Then there are some challenges if we want to apply these Gaussian conditional to neural nets. First is when we want to go from activation units to the hidden units on the subsequent layer. This equation that we saw previously, if we want to go from activation units at one layer to the subsequent hidden units, we need to multiply activation units, which are going to be Gaussian random variable, by Gaussian weights. And this product of random variable, which is nonlinear, doesn't have a closed form solution for, or at least it's not normal in the case of the product of Gaussian random variable. The second issue is that if we want to go from a hidden unit to an activation unit, we need that phi, that nonlinear activation function. And if z is Gaussian, passing a Gaussian through a nonlinear function doesn't have a closed form solution neither. Okay? And it's not going to be Gaussian neither. So what are the assumptions we need to do in order to enable or to overcome these difficulties? First assumption is that we're going to assume that all our weights biased in hidden units and activation units are Gaussian random variables. So everything in our network is going to be Gaussian. The second assumption is that when we take the product of activation units and weights, we're going to assume that this also follow approximately a normal distribution, where the parameters here, the mean vector and variance for this product term, can be computed exactly using what we propose in that paper that was published in JMLR, the Gaussian multiplicative approximation, which allow us, using the moment generating function, to find a closed form solution to evaluate these quantities. Then, when we have the activation function to go from hidden unit to activation unit, what we're going to use here is a local linearization using a first order Taylor series expansion of that nonlinearity in order to have an activation unit, which is going to be modeled by a normal Gaussian random variable. So starting from z, which is assumed to be Gaussian, we make a local linearization through the Jacobian of my nonlinear activation function in order to go from hidden units to activation units. Okay, and that local linearization is centered on the expected value of the hidden units. So at the end, what all this allows us to do is to model the joint between vector of activation unit at layer j plus 1 and all the parameters involved at theta j. So we can build the joint for these two quantities using a multivariate norm. Then we need to do some additional assumption in order to enable the scalability. In terms here, it means having a linear computational complexity with respect to the number of weights. So first, we need to assume that we have diagonal covariance structures for the parameter theta for each hidden layers, and also for the hidden units in each layer as well. Then we need to make the assumption that the hidden units zj are statistically independent for the parameter theta j. And finally, we need to leverage the inherent conditional independence that is built in neural network. What does it mean? It means that the hidden layer zj minus 1 is statistically independent from a hidden layer j plus 1, given the knowledge of the hidden layer zj. Okay? And this is not an hypothesis. This is built in the architecture of neural network. Okay? If I know everything there is to know about my hidden layer zj, these two, zj minus 1 and zj plus 1, are really conditionally independent because there's no arrows skipping in between those hidden layers. So at the end, what does it allow us to do is to have covariance matrices that define the dependencies, say, between the input layer and the first hidden layer, that have a very limited size because we can only store these covariance matrices for pair of subsequent layers. Same for the covariance between my parameters in hidden layers. These covariance matrices are going to be heavily sparse, really keeping in check the computational complexity of my method, because I'm going to do all my calculation and all my storing only for pairs of subsequent hidden layers. And then when it's going to be the time to do the inference step, I'm going to go from my observation and infer what would be my output layer for my last layer in my neural net. And then I'm going to do this. I'm going to propagate backward this knowledge in order to infer what are the values of my parameters as well as my preceding hidden layer. And I'm going to go back like this recursively through my network. And to do this, we're going to build our equation on the RTS estimation, okay, that is commonly used in state space model, for instance. And all of this has a linear complexity with respect to the number of parameters in my network. This is the same computational complexity as backpropagation. One last thing we need to see is that we need to estimate not only the parameters, but also the hyperparameters of my network. What does it mean? Is that we have some prior knowledge in Bayesian estimation. So our prior knowledge defined what is our knowledge for the PDF for describing our weights and bias. And initially in neural net, when we initialize that prior, it's going to be weakly informative. So for instance, our prior for theta is going to be parameterized by eta superscript 0, meaning this is our prior knowledge, okay, our initial knowledge before seeing any data. And typically this distribution, or at least in the case of TAGI, it's used as a normal, okay? And this mean vector is going to be initialized randomly, and this covariance matrix is going to be initialized so that it provides a weakly informative prior knowledge. And all this mean vector and covariance matrix is going to be regrouped into the vector eta of hyperparameters. But the problem is that the performance of TAGI depends on our choice of hyperparameter. So what we could do to solve this problem is to do a full Bayes approach, where we learn not only the parameter theta, but the hyperparameter as well, where we're going to have the likelihood, the prior, which now explicitly depends on eta, and we would have a prior for eta. But this full Bayes is not analytically tractable, so we cannot directly rely on it. We could say we're going to rely on empirical Bayes when we're going to try to maximize the numerator here as a function of the hyperparameter to find optimal values for a hyperparameter. The problem is that this would require to solve an optimization problem. And in the first place, this is what we want to avoid to do. We don't want to use backprop, we want to do only analytical inference. So here what we propose to do is to use a recursive approach, okay? So we're gonna use our first randomly defined hyperparameters. Then we're gonna use the data, we're gonna make the inference with TAGI, we're gonna update these hyperparameters. And then recursively, we're gonna use these updated hyperparameters as my prior. And I'm gonna see the data once again to have newly updated the hyperparameter. And we're gonna do this, use TAGI recursively over multiple epochs, and we're gonna stop looping like this using a validation set in order to make an early stop to avoid overfitting. Okay, one more question we need to address. Okay, everything we see so far is about feed-forward neural net. Can we use TAGI for CNN, scans, deep Q network for reinforcement learning architecture? The answer is yes, okay? Because all these more advanced architectures involve exactly the same operation as feed-forward neural network. And also, they're all compatible with the conditional independence hypothesis between layers. So all the calculations we solve for feed-forward neural net are also compatible with more advanced architecture. And if you want more details about this, we can look at these two preprints: Analytically Tractable Bayesian Deep Q Learning and Analytically Tractable Inference in Deep Neural Network, that are both available on arXiv. To give you a little example, we can see here how with TAGI we can get the computer to play an entire game. Here it's Pong, so you see that the agent is the green paddle here, which easily beat the computer presented on the left here. And here, this is really a joint application of convolutional neural network, because the agent really see the pixels that you're currently seeing at the screen, and reinforcement learning with categorical action. So the agent has to choose in between moving left or moving up or moving down. Okay, now let's get in the core of what is the talk today. So how can we leverage the hidden state inference capacity of TAGI in order to enable new capacity, new possibility within neural network? The first one we're going to look at is how can we generate through analytical inference adversarial attacks. So first, what is an adversarial attack? Here we have an example of an image of a 2. So I assume this is clear for everyone. This is unambiguously a 2. And if we train a neural net to see this image and to predict what is the label, we can easily reach a very high probability. So let the network say with a high probability that when it sees this, it classifies it as a 2. But what we can also do is that if we perturb this image with some like perturbation as represented here, and we add it on top, we can generate an adversarial attack, which means that if the computer sees this, he's going to say there's a very high probability that this is not anymore a 2, this is a 6. Whereas for a human, this is still unambiguously a 2. Okay, this is what is called an adversarial attack. And in typical neural networks relying on gradient backpropagation, the perturbation that I showed here is obtained through optimization, meaning we find a perturbation as the argument delta that minimize this, the difference between the label predicted by the neural network and the target label we want to reach. So we're looking for the perturbation delta that adds up to the initial input image, and that is going to lead to a misclassification. So this already exists, but what I want to look at with you today is how with TAGI we can do the same thing, but without relying on an optimization problem. We can directly leverage analytical inference to make adversarial attacks. So how it works, we're going to split it into a training phase and an attack phase. So with TAGI, first we train the neural net. So imagine we start with randomly initialized weight and bias. So the network hasn't learned yet. So we feed a first image. So we're going to propagate through the network that first image. So initially, since the network hasn't learned, it's going to predict a wrong label. For instance, it's going to predict a 7. Then we're going to provide the label from the training set. And then we were going to correct. So you see initially it was a 7. We see a 2. It's going to here correct the prediction on the output layer, correct the parameter value leading to this, and it's going to infer recursively all the correct information back onto the first set of weights and bias. Then we're going to repeat this with multiple image over multiple epochs. Okay, so at the end, when we present a 2 like this, the network is going to correctly say this is a 2 with very high probability. Then, assuming that we have our trained network, we can do an attack. So what we're going to do, we're going to add some uncertainty through adding a non-zero covariance on our input layer. Instead of being a deterministic input layer, it's going to be a probabilistic one. So the mean vector is going to be the color you're seeing here, and we're going to have a non-zero covariance to represent the uncertainty we might have about the input layer. We're going to propagate forward this knowledge. So since the network was correctly trained, the output is going to be a 2. So if it sees that image, the network is going to say at the end, I classify this as a 2. But with the attack, our goal is to have the network not say it's a 2, it's for instance to say it's a 6. So when we're going to use this label, we want to go back and propagate backward this knowledge, but we want to do it not to modify the weights of the network, but to modify our input layer. Okay, so here, if you look, there's some slight difference between this one and this one. There have been some minute pixels that were changed so that these changes are going to fool the network into saying this is not anymore a 2, this is now a 6. So if now we propagate forward this new 2, which has been slightly modified, then our network is going to classify it as a 6, whereas the original 2 still classify as a 2. Keep in mind that here I made a little shortcut in the explanation. We don't usually do this in one step. We're going to do this in multiple iterations, where the slightly modified 2 is going to be, again, propagated forward. We're going to assign a label 6, and we're going to go back. And we're going to do this over multiple iterations to reach really high probability of fooling the network. So here's an example of how it looks like. So what you can see on the diagonal is all the original images. So then we see that the original image was 0, it was correctly classified as 0. The original image is a 6, it's classified as a 6. And all the off-diagonal images you see here are images that were generated to fool the network. So this is classified as an 8, even if visually it looks like a 4. This was for the AMNES dataset. We have the same thing here for the CIFAR 10 dataset. So if we summarize these results, we can see that for convolutional architectures, for AMNES or CIFAR, so for AMNES, if we have no attacks, so just train the networks, we can correctly classify these digits with an error rate of 0.64%. For CIFAR, it's a harder dataset, it's 22% error rate just by training the network. But then if we decide to do a targeted attack, meaning that we want to obtain a specific wrong class with the network, so we give an image of a 2, we want to achieve a 6, with a specific label on the target attack, we can reach for AMNES 99.8% error versus 99.6. So we can fool almost 100% of the time the network. And if instead of having a targeted attack, so I just want specifically a 6, I say I want any label but the correct one, then we can achieve error rate of 99.9. Okay, now let's look at a second problem where we can leverage the inference capacity of TAGI. What we want to do is to use a neural network as a black box optimization tool, okay? So imagine that we have a regression problem where X is the input covariate and Z output is the output of the neural network that's intended to model an observed response. So we have here X the covariate, Y the observed response, and this is the reality we want to model. In this case, it's the deterministic X cubed minus 3X. So how would it work in a training set? We would start by seeing a first observations. So this is our first observation at covariance minus 1.5. We propagate forward the knowledge. Here we would see something like 1.1. So we would correct all of our parameters, the hidden layers in the network using this. And then we would move to the second observation, say 0.5. We would observe the observation minus 1.3. We would learn the parameters of that neural net. So if we repeat that for a large number of observations, we can see that at the end, we're going to learn what is the function. So the black line is the truth, and the red line is underneath with the confidence interval represent the expected value that is provided by the neural net, as well as the confidence interval, which represent the uncertainty associated with the weight and bias among the network. But the key aspect of neural net, or one key aspect, is that not only it allows, once we've learned a function, to have the information about the function itself, but also its derivative, okay? Because all the information that's encoded here also include the information using the same weights and bias about the derivative of the function. So here, since we know what is the equation of the function, we can know what is the theoretical true derivative of that function, represented again in black. And what we have in red now is the derivative of that function as approximated by the exact same weight and bias that were learned for observation of the function itself. And this is not specific to TAGI. This is true with any neural network. But now what we can do is that we can use not the network associated with the function on top, but the network we see on the bottom associated with the derivative of the function, and do inference on that network, okay? For instance, what would happen if I start at a covariate minus 1.5 represented here? I would propagate this forward to obtain what my network for the derivative predict. Here it's going to be something around 4, okay? Then what I'm going to do, I'm going to say, I want you not to use the 4. I want you to tell me what should be the input value so that my output is 0. And the specificity is that here, the derivative of a function equals 0 when it's either a max or a min. So what I want to do is to say, I don't want to have minus 1.5. I want you to find me what is the x coordinate so that the derivative is 0. So either that max or that min. So in that case, we say this is 0. Find me what is the input covariate. So in that case, it's going to find minus 1. That minus 1 corresponds to y prime, or derivative is 0. This is the max of the function here. And keep in mind, again, we're not doing it in one shot. We have to do it over multiple iterations to move towards that maximum of the function. We could do the same thing. Instead of starting at minus 1.5, we could start at 1.5, where, again, the derivative is around 4. And instead of using the value 4, we say what we observe is not 4, it's 0. And we're going to update our hidden layers until we update our initial value. So instead of being 1.5, we're going to reach 1. So 1, we have the derivative which is equal to 0. This is going to correspond to our min. And the equation to do these update steps are the exact same equation we had in TAGI. Okay, basically these equations are a function of the prior knowledge for the position mu x, so the covariate here. We have the covariance between the derivative on the output layer and our input. This is the prior variance for our output layer for the derivative, and this is the prior mean for the derivative of the output layer of the neural net. And all these quantities are the same here. This is for updating the expected value of my input. This is for updating the variance. But here, one issue we have is that we cannot select whether we want to reach the max or the min. We're just going to reach the one that is closest to it. So if we want to guarantee we're going to reach a max or a min, what we can do is that to add these absolute value between this correction terms that change my expected value, add the sign of the derivative of my neural net and a factor alpha. And with the factor alpha, I can control whether I want to reach a max if alpha is greater than 0, or a min if alpha is lesser than 0. So if we look at this in action, we can say that in the first case, we're going to disregard this modified formulation, directly use these equations without the alpha. So in that case, if I start at an initial value mu x equals 0.25, so 0.25 is somewhere around here. So here, if we perform the inference to find where is my derivative equal to 0, we're going to find that the derivative is equal to 0 at 0.96, so close to 1, which represents the min. If I do the same thing, but start at minus 0.25, so minus 0.25 around here, somewhere here, we see that we reach derivative equals 0 to minus 1, so the max. Okay, so here, if we don't have the alpha formulation, we're not going to be able to select whether we want to reach a max or a min. Now, if we use the modified formulation with the alpha, if we set alpha equal plus 1 and we start at 0.25, we're going to reach -1. So we're going to reach the max. If we use minus 0.25, we start here, we also reach -1, which corresponds to the max. So by using a positive value for alpha, it's going to guarantee that we reach the max. On the opposite, if we use -1, we start at 0.25, we're going to reach +1, the min. Same thing if we start at -0.25, we reach the min as well. So we can here use a positive or a negative value for alpha in order to control, are we looking for a max or a min? Okay, so this is a very trivial problem. So obviously the goal of this method is not to find the min and the max in such a trivial function. The goal is to leverage the capacity of neural networks to learn the topology of complex functions in high-dimensional space and be able, as we learn the function itself, to find what are either their max or the min. And the key application of this is through reinforcement learning, okay? Continuous action reinforcement learning. And in order to, before seeing continuous action reinforcement learning, let's look quickly at reinforcement learning for categorical action. So the example of Pong we saw earlier is an example of reinforcement learning done for categorical action. So here we're going to use a neural network in order to map a state. So the state is the pixels the agent sees here. We're going to pass that through a neural network, and the output of the neural network is going to model the expected value for being in that state and taking an action, where here there are two possible actions. So for the input, which are the pixels here, the network is going to have two outputs. The expected value for action 1 going up, the expected value for going down, action 2. So these are the two possible actions. This is why we say it's categorical action. It's either action 1 or action 2. In that case, we're going to have two outputs on our neural networks, where in the case of TAGI, these two outputs are going to be Gaussian random variables, describing what is the uncertainty about the expected value for action 1, same thing for action 2. And when it's going to be time to select which is the optimal action, going up, going down, what we're going to do is rely on Thompson sampling. So we're going to take one sample from that Gaussian random variable represented in blue. We're going to do the same thing for the Gaussian random variable here for the going down. And we're going to say the optimal action A star is the action that maximizes either of my two samples, okay? And then when it's time to learn the parameter of such architecture, we're going to rely on temporal difference learning, where we can put in relation the value of two consecutive steps with the reward perceived by the agent. So all the details about this are available in the paper I referenced to earlier in the presentation. So that are still represented here. So analytically tractable Bayesian deep Q learning. So this is for the case of categorical action. And the key here is that once we want to select the optimal action, we can simply pick between the categories of actions. We can compute what is the expected value for each of them, and then we simply pick the max among a fixed set. But this is slightly different if we want to do continuous action reinforcement learning. Imagine we would like to steer the wheel of a car, okay? If we don't want to discretize into a subset of fixed angle for the wheel, we want to consider it as a continuous variable, which represents an infinitely many number of possibilities at which I can rotate the wheel. So in that case, I cannot anymore just have infinitely many output nodes here. So what I have to do instead is, if I want to consider all these possibilities of wheel's angle, is to put my actions, which is going to be the wheel angle, on my output layer. Okay, so here now I'm going to model my expected value for being in a state, so what the car cameras would see, and the action, the angle of the wheel. So depending on the action taken and the state of the world, what is the expected value in being in that situation? But in such a case, how do we define the optimal value or the optimal action? Backprop trained networks that use continuous action are going to rely on the gradient of the expected value with respect to the action in order to guide where should be the optimal action. So they use gradient-based approach in order to optimize which action should be taken. But here, what we want to do with TAGI is to avoid relying on gradient-based methods. So what we're going to do is that we're going to take advantage of the capacity to learn from constraint. And here, as we saw with the optimization problem, we can say, I know the best action, the one is going to satisfy the constraint, that the derivative of my output, the Q value, the expected value, with respect to the action, is going to be equal to 0. So by setting this constraint, I can infer what is the action here that's going to lead to the best performance. And then what we can do, we can couple what was here as a value network, the net Q, that represents the value of being in a state and taking an action. And we can couple this with a policy network, the net A. The policy network say, given the same state, what should be the action I take? So that we can see that these two things are the same thing. So if I know the state of a system, I can have a policy net that's going to readily tell me what should be the action taken. Once I know the state and the action, I can predict what is the value of being in a state and taking an action. So at the end, we learn in 2 steps. In the first step, we're going to use temporal difference learning, as we did with the categorical action reinforcement learning, or deep Q network, to learn the parameter of that value net, that net Q. And at the same time as I'm going to be doing this, I'm going to infer the derivative of my Q network with respect to the action should be equal to 0, to infer what should be the action taken here. Once I have inferred what should be the action here, I use that knowledge to update my policy network, its parameter. And by doing the same in a recursive way, we can learn simultaneously our net A, the policy net, as well as the net Q, the value network. And if we look at this, how it works in practice, we have here the AF cheetah game from the Mujuko environment. So this is how it would look like if we play at random. So before learning, we have a cheetah. That cheetah needs to run. So you see initially, by trying to control all the angle of the articulation of that cheetah, it initially does a really poor job at running, okay? So here it doesn't work. So what we're gonna use is we're gonna use TAGI in order to learn by interacting with the environment, what should be the angle and movement of all the articulation so that our cheetah runs. So after 1 million interaction with the environment, this is what TAGI achieves. So we see that now that AF cheetah really is capable of running and moving forward successfully. So if we compare with existing approach, we have on the horizontal axis the number of interaction in million steps. In the vertical axis is the average reward. So what you can see here, all the results are presented for the average of 5 runs. And we have in red TAGI, where we can say that match or exceed the performance of existing approach, either PPO, Actor Critic, ACKTR, and TRPO. Okay, so here our claim and what we want to show here is not necessarily that we can beat the state of the art or we're better than any method. What we want to show is that with TAGI, we open completely new realm of way of seeing at the inference in neural network. We don't have any more to rely on gradient-based approach. We can really leverage the capacity to make analytically tractable inference for either the parameter or the hidden states of neural networks. So in conclusion, what I've presented here is that TAGI is a powerful tool that allows analytically tractable hidden state inference in neural network. And that enables paradigm shift application or paradigm shift conceptual understanding of how can we perform inference, either in inference-based adversarial attack, inference-based optimization, where we use a neural net as a black box optimization tool. And this is what enables the continuous action inference-based reinforcement learning.